Two identical servers, same network card, same software, same traffic. One of them handles roughly double the packets per second of the other. Nothing in the configuration file explains it. The difference is physical, and it starts with a single arriving packet. The packet lands on a network card. On a big server, that card is not floating in the middle of the machine. It is plugged into expansion slots that belong to one specific processor, and that ownership matters enormously. Here is that owner, socket 0, the first processor. A two-socket server is really two computers sharing one case, one power supply, and one operating system. Each processor has its own memory and its own slots hanging off it. This is socket 0's memory, the bank of RAM wired directly to that processor. When the card copies an incoming packet into memory, this is the memory it reaches, because this is the memory physically nearest to the card. And here is the second processor, socket 1. It runs the same operating system and the same application, but it sits on the other side of the machine with its own memory and no direct wire to that network card. Between the two processors runs a private link. Anything one socket needs from the other socket's memory travels across it. The link is fast, but it is not free, and it is not the same as reaching your own memory. Finally, the lever you actually control, an affinity rule. It is simply a decision about placement, telling the card's queues and the application threads which processor to live on. One setting and the whole picture changes. The tension is this: nothing stops the operating system from running your packet processing thread on the far processor. When that happens, every packet takes a detour, and the cost only becomes visible when the server is actually busy. Let us follow one packet. It arrives on the wire and hits the network card. Everything from this instant onward is a question of geography, how far the data has to travel inside the machine before work happens. The card does not hand the packet to a processor. It writes the bytes straight into main memory by itself, and the memory it can write to is the bank attached to the socket its slot belongs to. So the packet now physically exists in socket 0's memory. Nobody chose that. It followed from where the card is plugged in. The data has an address in the machine long before any software looks at it. Now the good case. The thread that reads that packet happens to be running on socket 0. It asks for the data, and the data is already in the memory next to it. Short trip, low latency. Notice what makes it fast. The card, the memory holding the packet, and the core doing the work all sit on the same side of the machine. Nothing has to leave that neighborhood at any point. Now the bad case, and it is the default. Nothing told the scheduler where to run your application, so it lands on socket 1, the processor with no wire to that network card at all. The packet is still sitting in socket 0's memory, so this processor cannot simply read it. Its request has to leave the socket and travel onto the private link that joins the two processors together. Across the link into the far bank of memory and then all the way back with the answer. It works perfectly. It is simply a longer road, and every single packet now drives it. For one packet, the detour is invisible, a handful of nanoseconds. Multiply it by millions of packets a second and the link stops being a detail. It becomes the narrowest part of the whole path. This is why the symptom is so confusing. At light traffic, both servers look identical. The gap only opens when the machine is busy, exactly when you least want a mystery, and it can have throughput. The fix is not a faster card or more memory, it is placement. You pin the work to the socket the card lives on so the packet and the code that reads it stay neighbors. That means two things pinned together. The cards receive queues, get their interrupts steered to cores on the near socket, and the application threads that drain those queues are pinned to the very same socket. Pin only half of it and you gain almost nothing because one side still reaches across. Get both onto the near socket and the link goes quiet because nothing on the packet path needs it anymore. How do you know which socket owns a card? The operating system will tell you. Every device is labeled with the processor it hangs off, and every memory bank is labeled with the processor that owns it. None of this is a defect. Splitting memory between processors is precisely what lets a server have many cores at all. A single shared memory bus for everyone would have become the bottleneck years ago. 2 cards, 1 per socket is the common answer at scale. Each card feeds the processor beside it, both halves of the machine stay busy, and no packet ever has to cross the middle. And this is why your laptop never shows it. 1 processor, 1 memory bank, no far side to reach. The problem is born the moment a machine gets a second socket and grows with every extra one. So the whole picture. The card belongs to 1 socket, packets land in that socket's memory, and a thread on the far socket pays a crossing for every read. Pin cues and application to the near socket. Hidden machinery shown. Next time a server refuses to scale for no visible reason, ask which processor is touching the packets. The answer is often geography, not code. Follow how it all runs for more. See you next time.